Hello friends, welcome to today's lecture Stress and Strain. Myself Mr. Y.S. Patil, Department of Civil Engineering, Sharad Institute of Technology, College of Engineering, Yadra. Before starting with lecture, we just discuss about syllabus. Mechanics of solid. Exam scheme for this subject is 20 marks for continuous assessment, 20 marks for mid-semester exam and 60 marks for end semester exam. In syllabus, total 6 chapters is there. First one, stress and strain. In stress and strain, types of stresses, types of strain, then Hooke's law, stress strain curve for MS bar, then uniaxial, biaxial and triaxial deformation, relation between three elastic modulus, and numerical based on these points. Second one, shear force and bending moment. In this chapter, we calculate or draw that SFD and BMD for simply supported beam and cantilever beam subjected to UDL, point load and moment. Third chapter is stresses in beam. In stresses in beam, that is first bending stresses in beam, shear stresses in beam and torsion. In fourth chapter, column and strut. Column and strut using Euler's theory and Rankine's formula. The fifth one is combined stresses. It is nothing but principal stresses in beam. And last one is theories of failure. In theories of failure, that is principal stress theory, principal strain theory and strain energy theory. So let us see chapter number 1, stress and strains. In this lecture, we studied mechanical properties of material, stresses and its type, strain and its types, Hooke's law, stress strain curve for mild steel bar and numerical based on this point. So first, mechanical properties of material. That is first property, elasticity. It is a property of material by virtue of which it regains its original size and shape after removal of external load. Means when you applied load on a body, due to that external load, the body is deformed, and after removal of this load, the body try to regain its size and shape. That property called as elasticity. The next one is plasticity. It is a property of material by virtue of which it does not regain its original size and shape after removal of external load. Means when you apply load on a body and some deformation occurs due to that external load, after removal of that load, the body does not regain a size and shape. That property called as plasticity. The next one is malleability. Malleability, it is a property of material by virtue of which it can be rolled into thin sheets. When you applied load on a particular material and that material converted into thin sheets, that property called as malleability. The next, ductility. Ductility, it is a property of material by virtue of which it can be drawn into wires. Then hardness. It is a property of material by virtue of which it resists indentation, scratching, abrasion. Means hardness means you just easily identify any material hard or soft by just scratching by using your nails. That property called as hardness. Brittleness. It is a property of material by virtue of which it break into pieces without any prior deformation. Means brittle material, when you applied load on a brittle material, it fails without any deformation. The best example for brittle material is glass. When you applied load on the glass, it break into pieces suddenly. That's called a brittleness. Strength, it is a property of material to resist load without breaking. That is tensile strength, shear strength. Means the safe load carrying capacity of material, it is nothing but strength. Then toughness or impact strength. It is a property of material to absorb energy without fracture. Means the energy absorption capacity of the material is nothing but toughness. Fatigue. A material many fails under cyclic load even even through maximum applied load is less than load of the material under the static condition. Means a continuous cyclic loading means repetitive loading acting on a particular material and the material fails under that cyclic loading, that called as fatigue. Then next, stiffness. It is ability of material to resist elastic deformation. And last one is creep. Creep, it is a continuous deformation of material with time when the material undergoes steady external load. Means the material fails under steady and continuous long time loading condition, that called as creep. Stress and its type. First one, direct stress. When a force applied to an elastic body, the body deforms. The way which the body deforms depends upon types of applied force to it. Means basically two types of forces. First one is a tensile force, second one is a compressive force. See this figure. In this figure, F force acting on a body, and that is a pull in nature. That means tensile in nature. So when applied on this body, the change in length is increased due to this F force. So that particular tensile force produces tensile stress, and body change in length increases to that the original length. In this second condition, the load F is push in nature, that is compressive in nature. So compressive force produce compressive stress, and the change in length is, or that final length is less than that original length. So body will be shorter one. So definition of the stress is resistance offered by the material per unit cross sectional area is called as stress. So tensile stress, compressive stress, it is a direct stress. So mathematical expression is stress is equal to force upon cross sectional area, that is P by A, and it is denoted by sigma, and the unit of stress is Newton per mm square, Newton per meter square, or Pascal. Then types of stresses. First is direct stress, means that is tensile stress or compressive stress. Second one is shear stress, and third one is bending stress. Strain. Strain means when you applied load on a particular body, the body will be deformed. Suppose when you applied load on this fixed section, tensile force, so change in length will be increase in length. So this green part is original length and yellow part is a change in length. So strain, definition of the strain is deformation per unit of the original length, means change in length to the original length. It is denoted by small e. Change in length denoted by delta L, and L will be the original length. So strain is equal to delta L by L, and strain is a ratio, that's why strain has no unit. Types of strains. First one is a linear strain, second lateral strain, third shear strain, and fourth volumetric strain. Next, Hooke's law. We know that the Hooke's law, what does the Hooke's law state? It states that within elastic limit, stress is directly proportional to the strain. Means within elastic limit, stress and strain is directly proportional to the each other. So sigma is directly proportional to E. So sigma is equal to capital E into small e. So capital E is equal to sigma upon E. It is nothing but E is equal to Young's modulus. Sigma is equal to stress and E is equal to strain, means Young's modulus E is equal to stress upon strain. So equation number 1. So by using this, we know that sigma is equal to P by A and strain is equal to delta L by L. This sigma and E value put up in this equation number 1. So we got a new equation, that is change in length is equal to delta L is equal to PL upon AE. This is we got new equation. So let us see stress strain curve for steel. So when you test a tensile test on the steel bar and dictate the load and change in length, and plot a graph stress versus strain on the x-axis strain and on the y-axis stress. Put up all points and you draw a graph. The milestone bar graph will be like this: O, A point, B, C, D and E. So OA is the initial region which is in a linear proportion, means O to A is elastic limit, Hooke's O to A elastic limit, that is O to A stress is directly proportional to strain. Then A to B is the elastic limit, means from beyond the point B, when you remove the load, the material regain its size and shape. Then B to C is a yielding, means when you see this graph, B to C only increases strain without increasing stress, means only the bar will be elongated without carrying the load. Then C D is a strain hardening, means C to D strain also increases, same time stress also increases, means length is increased and also load carrying capacity also increased. And DE is a further stretching leads to reduction in applied load and fracture. When you take a tensile test on the steel bar, the failure pattern is cup and cone formation or neck formation, means one end is like cup and other end is like cone. So that formation is neck formation. So let us see one example. A steel rod of 800 mm length and 60 by 20 mm in cross sectional is subjected to axial pull of 100 kN if modulus of elasticity is 2.1 into 10 raised to 5 Newton per mm square. Calculate stress, strain and elongation in rod. So first of all, write out given. So given value will be length is 800 mm, width of the section is 60 mm, depth is 20 mm, cross sectional area for that section is 60 by 20 is equal to 1200 mm square, and applied load is 100 kilonewton converted into Newton, that is 100 into 10 raised to 3 Newton, and the nature of the force is tensile, and Young's modulus E will be given is 2.1 into 10 raised to 5 Newton per mm square. So determination is we require to find stress sigma, strain E and elongation delta L. So first of all, to find out stress, we know that the stress is equal to load upon cross sectional area. So load is equal to 100 into 10 raised to 3 and cross sectional area is equal to 1200. So your stress will be 83.33 Newton per mm square. This is your answer. Then next, to find out strain. Strain is equal to change in length upon original length, and we know that by using Hooke's law, that is Young's modulus E is equal to sigma by E. So the strain is equal to stress upon Young's modulus E, and we already calculated stress and we know the value of the E is already given in the problem. So strain is equal to stress upon Young's modulus E, that is 83.33 divided by 2.1 into 10 raised to 5, and your answer will be 3.96 into 10 raised to minus 4. The strain is a unitless quantity, so final answer for strain is equal to 3.96 into 10 raised to minus 4. Then elongation in steel rod, that is change in length delta L. By using formula we know that formula is delta L is equal to PL upon AE. We know the value of the P, we know the value of the L, area and Young's modulus E. Put up all values in this equation. So delta L is equal to 100 into 10 raised to 3 into 800 divided by 1200 into 2.1 into 10 raised to 5. So change in length will be 0.317 mm, and the applied force is tensile, so change in length also increase in length. So our final answer will be stress is equal to 83.33 Newton per mm square, strain is equal to 3.96 into 10 raised to minus 4, and elongation delta L is equal to 0.317 mm, that is increase in length. So next problem is, last problem we discussed about only uniform cross section of the rod. Now we see the different cross sections and different length of the rod. So let us one problem, new problem. A steel bar is 900 mm long. It is two ends are 40 mm diameter and 30 mm diameter, and the length of each rod is 200 mm. The middle portion of bar is 15 mm in diameter and 500 mm in long. If the bar is subjected to an axial tensile load of 15 kN, find total extension. Take Young's modulus E is equal to 200 giganewton per meter square. So first of all, draw the sketch. So overall length of the rod is 900 mm, and first part is 40 mm diameter having length 200 mm, and last part is 30 mm diameter and 200 mm length, and middle part is 15 mm diameter with 500 mm length. So AB is a 40 mm diameter, 200 mm length, BC is a 15 mm diameter, 500 mm length, CD is equal to 30 mm diameter, 200 mm length. So first of all, AB is a part 1, BC is a part 2, CD is a part 3. So L1 is equal to 200 mm, D1 is equal to 40 mm. So by using this D1, calculate A1. Area of round bar is pi by 4 into D square. So A1 will be 1256.6 mm square. Similarly for part BC, that is L2 is equal to 500 mm, D2 is equal to 15 mm. So A2 will be 176.7 mm square. For part CD, L3 will be 200 mm, D3 will be 30 mm. So A3 will be pi by 4 into 30 square, that is 706.85 mm square. And the applied force P is 15 kilonewton. So 15 into 10 raised to 3 Newton, and the nature of the force is tensile. So now E is given, that is 200 Gn per meter square. Gn means giganewton per meter square. So I want to convert this giganewton per meter square to Newton per mm square. So 1 giganewton is equal to 10 raised to 9 Newton. So first I convert this Gn into Newton, that is 10 raised to 9, and 1 meter square is equal to 10 raised to 6 mm square. So divide by 10 raised to 6. So our value of E is 200 into 10 raised to 3 Newton per mm square. Now I want to find out total extension, that is delta L. So I want to find out first delta L1, delta L2 and delta L3 for total extension. So delta L is equal to delta L1 plus delta L2 plus delta L3, and we know the equation for the delta L is PL upon AE. Suppose I want to find out delta L1, so equation will be PL1 upon A1E. Delta L2 is equal to PL2 A2 upon A2E. Delta L3 PL3 upon A3E. So final equation for the delta L is equal to PL1 upon A1E plus PL2 upon A2E plus PL3 upon A3E. Out of this total equation, P upon E is a constant term, so take outside of the bracket that P upon E, and in bracket L1 upon A1 plus L2 upon A2 plus L3 upon A3. And we know all values of P, E, L1, L2, L3, A1, A2, A3. So put up all values in this equation, and the change in length, calculate change in length. So delta L is equal to 0.245 mm. This is your final answer. So total extension of the steel bar is 0.245 mm. Thank you.